From wherever you are around the world, welcome and thank you for joining us. This is the Circle of Insight show, a show about everything in human behavior, and I'm Dr. Carlos. Today we're going to be exploring the world of autism. That's right, we have Dr. John J. Gargus, Professor of Physiology and Biophysics, School of Medicine. He's also Professor of the Pediatric School of Medicine at UCI, and now he's the Director of Center for Autism Research and Translation in the School of Medicine at UCI. Let's welcome Dr. John J. Gargus to the Circle. Welcome, sir.
Hi, Carlos. How are you?
Excellent. Thank you so much for coming.
My pleasure.
This has been a hot topic, but before we get started on the topic, because there's so much to cover, how did you get started on autism?
Oh, my training, I did an MD PhD at Yale, and my training was in human genetics. It was at the time when human genetics was just becoming at the level that it was a recognized program. It was the first year that there was a program there at Yale.
Oh, wow.
And in metabolic genetics, we're really looking at ways that the genes perturb health. And by and large, we've always worked with very, very rare mutations that cause very, very rare diseases. But sort of the paradigm has always been that those rare diseases will tell us how the common diseases come about and inform us how we can make therapies to target the common diseases. And so in evaluating kids in clinic, a lot of the patients that I would see had aspects of their problem that involved neurodevelopmental disorders. So that it's just a very, very common way when you have a multi-system disorder, a different kind of genetic disease, very commonly brain function and neurodevelopment get impacted. And so I would be seeing that phenotype a lot. And it sort of sequentially happened, a number of steps, but a lot of the diseases that I was seeing involved energy metabolism, a lot of mitochondrial diseases, and a lot of those had what we call comorbidity. Part of the disease was that they had an autism-like phenotype. And so we started looking at how these different components could fit into that. And our thinking about it over the 20 years that I've been here has really evolved quite a bit. But we had been involved with autism going back more than 15 years when we were one of the 10 U.S. centers that were the Centers for Excellence in Autism Research, the CPEA project that the NIH first launched to sort of systematize how we evaluate autism. So it was sort of a step-by-step process, and our thinking has evolved a lot over that time.
I'm sure it has.
I mean, just the impact of genetics on autism has been huge, and just over the relatively brief career that I've been in genetics, I mean, the time frame is that when I was in a training program at Yale, we had no ability to read DNA. The very first genome got sequenced by one of the professors there. It was 3,000 bases long. It was a little teeny virus. It took him, 2 labs full of dozens of postdocs for 2 years to do that. And now it's something that a student walks in the door and they'll do it the next day.
Really?
Yes. So the amount of genetic information that we have has just been enormously expanding. And it's now come to the point where it can inform how we understand the more complex diseases. And again, I wear those 2 hats you mentioned, both biophysics as well as genetics. I think putting them together is really critically important because the genetics just sort of tells us things that might be involved in the disease, but the biophysical process actually tells us how they're involved in the disease. And that gives you a window into how you might be able to treat it. And I think it's critically important that we look at the function of the genes, and that's something that our center has been very focused on trying to do.
And when you're saying function of the genes specifically associated with autism or anything?
Specific, if you want to just count every day you open the newspaper and there's an autism gene, right? And then what does that mean? It doesn't mean a whole heck of a lot of anything, because every day there's a blood pressure gene, and every day there's but most of those genes that get implicated have very, very weak effects on the overall body. So I would say more than 800 or 900 genes out of the 24 or 25,000. So this is a big chunk of genes have been implicated in autism. And all of them contribute a tiny, tiny sliver. There are a handful of genes that contribute a substantial amount, and we believe that by understanding the ones that can contribute a substantial amount, you can get a blueprint. We call it the genetic architecture of how the disease works. And that's what we feel. That's where we feel the actionable piece of information is, that if you understand that overall architecture of how the disease process comes about, you're going to be looking at the input of dozens and dozens of genes into what we call a pathway, into a mechanism that's going on in the cells. And that's where we see the potential for being able to get a therapy. We don't think that on a gene by gene by gene basis, you're going to get an informative signal. We don't think on a gene by gene by gene basis, you're going to be able to come about something that's going to be a useful treatment for anybody. We feel you need to look at a much more integrated picture. And that's why in the center, we've put together everything ranging from genomic information up through, routine clinical care, but clinical trials and all kinds of intermediate functional analysis of what the genes are doing in order to make sense out of what the whole pathway to disease is in autism.
Just to make sure I got it clear. So we have about 800 pieces of genes. We'll just say roughly, hypothetically, we have 800 pieces. That you think that makes the whole puzzle now?
No,
not yet. Okay.
And no, and the point is, a lot of people really care about finding all the genes that are involved. I think it's
Oh, really? Okay.
We don't need that anymore. I think we have enough information to be able to find a target that we can go after. What we can already recognize is that there are three big clusters of the kinds of genes that contribute to autism. Some of them are genes that cause DNA to fold up. So they're what we call chromatin modifying genes. And those, I wouldn't know how to target them specifically. And there are a handful of genes that are what we call transcription factors. They turn genes on and off. Again, those things work in dozens of different places. They're very nonspecific, very hard to target. I wouldn't know how to do something with them. The subset that we're interested in is a very important one, and that's the signaling molecules that sit in cell membranes. So cells talk to one another through a very special form of electricity, ionic currents across their membranes, and that is very actionable. It's the kind of thing that we make drugs for that treat heart rhythms, the strength with which a heart pumps. It's the kind of thing that we use to treat seizures. So we know how to make very specific drugs that target those kind of molecules. That seems to me to be the sweet spot. That's one of the areas that we feel is very important to be focused on in terms of looking at a place where you might be able to do something specific enough to actually help some kids.
Sounds extremely hopeful.
Well, I mean, we think it is comparatively hopeful. I think a lot of this thing about talking about the architecture of the disease tells us that this is meaningful because the same kinds of genes, and something that I've written about pretty extensively, is that the disease processes that we call seizures and that we call migraine, they don't look alike. They don't look at all alike to us, to our eye, to our clinician's eye. But if you look at the genes that are involved, you can mutate a gene in one spot and you can make a migraine, and you can mutate it in a different spot and you can make a seizure.
Really?
And you can mutate it in a different spot and you can have autism. So that's very informative because we really do understand how seizures come about. And we really do begin to understand migraine. I mean, again, it was a paradigm shift. Again, how one of the transitions of getting into the autism was migraine for me. We worked on migraine for a while. And you mechanistically can understand how a disease that looks very cryptic, like migraine, used to be called a vascular headache, which
That's right.
It can't be. None of our genes are expressed. None of the genes that are involved in the migraine that we studied, these rare forms of migraine, are expressed in the vasculature. They're expressed in neurons, and if you mutate them in different ways, you make seizures. So it says migraines are a lot like seizures, and therefore it makes sense why some of the same medicines that you use in seizures also work in migraines. They're very similar. They don't look similar to us. In the same sense, the autism mutations, again, very, very rare sets of autism mutations, also do the same kinds of things, which suggests that it has something to do with making a set of the neurons hyperexcitable. It makes them like the kinds of mutations that we see in cardiac arrhythmias and those kinds of disorders. And again, it sounds like you're mixing apples and oranges and grapefruits. I know, but in terms of the underlying mechanisms, the genes tell us that these processes are very closely related to one another. And that's what we're trying to dig into and make a little more sense out of.
Wow. Yeah.
So, yeah.
That's amazing stuff. So we're targeting these genes, but are you able to, so right now you're able to look at where the action's coming from. You kind of discover where the action is, where the functionality of it. Are you getting more of an understanding of that?
So our center is very new. So the Thompson Family Foundation here in Bill and Nancy Thompson here in Irvine creatively came up with an ability to help people in autism. They wanted to do what they called entrepreneurial philanthropy, and they put together a consortium of people that involved the Children's and Family Commission, the county commissioners, a whole host of people to put together. And ultimately, they put together a pool of $14 million up front and ongoing funding of another 14 that kept our clinical center and research center going in Orange County. It is a incomparable resource for Orange County because in most places, autism centers only see you if you can pay cash and walk in the door with cash.
Oh, really?
Whereas here, we will take insurance, we'll take regular care and all that kind of stuff. So we think that from the research point of view, that's important because we're seeing typical autism. We're not seeing, but it's also very important for all the families that are here in the community that because of this investment, not only are we able to diagnose the autism, but we're able to actually go on and treat it. Under the tobacco tax, the Proposition 10 tobacco tax launched our autism clinical program, which used to be called 4OC Kids and now is the Center for Autism and Neurodevelopmental Disorders. That center, that program, it's up here on Red Hill Road. It's right in our neck of the woods here. and that program is really critically important because while the tobacco tax mandated it to diagnose autism, diagnose diseases that would impact their early 1 through 5 learning experience. They never had funds for treatment. Now the obligation is for putting together treatment programs. So that's very important. But if you look at the frequency of autism and you look at the costs of autism, nationwide it is an unsustainable trajectory. I mean, it's hundreds of billions of dollars.
Wow.
And so it's exponentially increasing for reasons we don't really completely understand.
You mean the autism diagnosis?
The diagnosis of autism and the costs to maintain autism programs around the country. So somewhere we're going to reach a break point. So while it's critically important that we're immediately doing things to help the families and the kids here in Orange County right now, it's not going to be enough. We have to come up with a game change. We have to come up with some kind of a therapeutic intervention that's going to have as dramatic an impact on autism as my paradigm always is this new discovery in cystic fibrosis, where that drug discovered just down the road in Vertex here in Southern California, molecularly cured the defect that causes cystic fibrosis. It's a very different thing than treating the symptoms of the disease, which by and large is what we're doing now in autism. We're trying to make the situation better, but we're not trying to go to the root cause of the autism. And that's very much what we're targeting. We believe that the genetic lesions are telling us what the root cause is, and we're taking our lead from where we want to target based on those original signatures that we get from the genetic lesions that we see.
Hello, my name's Matt, and I'm an addict.
My mom was addicted to prescription pills when I was very young, before I even turned 1.
Are you or someone you know struggling with alcohol or drug addiction? Has everyone given up on you or your loved one? The caring staff at Elite Care understands and treats you as a whole person. We offer individual and group therapy, holistic healing such as yoga, nutrition, and spirituality, medication management, and PTSD treatment. By building upon your strengths and rebuilding broken bonds, we help you begin a successful life. With our staff of licensed psychotherapists and doctors, you can be assured of the highest level of care. Elite Care is the best option for long-term rehabilitation from drugs and alcohol. Contact 888-511-0607 for more information.
When you've identified all these genes, hundreds of genes you were mentioning, little
And again,
slivers.
we've not identified. This
Somebody
is the
did.
whole world community that's been
Not just
doing
John
it.
J. Gargus.
No, not at all. No.
right.
Yes, right. Yes.
But does it change? I'm trying to see how I can phrase this. I want to keep it simple in my head.
Okay.
We got 800 genes. Well, I'm just going to hypothetically make it up.
Right.
800 genes of autism. Are those the same makeup for the spectrum of autism? Or do they vary?
Well, and I'd say it's not a distinction that we can make meaningfully. Certainly not yet. And again, what's happening, and this is something that's happening pretty much globally in all of medicine, and this is this trend towards personalized medicine. And the paradigm for all of this has really been cancer. And I mean, cancer is 10 to 15 years ahead of autism, but the genetic architecture is exactly the same. That is, you may find that two women who have a breast cancer share certain marks, genetic marks, that we found to be very important. So people might have heard the term HER2/neu, or they might have heard estrogen and estrogen positive, or so those kind of marks tend to cluster some of the tumors together, and that indicates what might be the most appropriate treatment for that subset versus another subset. But when you drill down and do what we're now doing, and again, what's mostly being done at the cutting edge of cancer therapy is that you take the genomic DNA, the DNA from the whole person, and you sequence it, and you take the DNA from the person's cancer and you sequence it, and you look what changed in the cancer compared to what was there in the rest of the body. And that has in many cases led to the targeting of new drugs. They say, well, this isn't a drug we usually use in breast cancer, but we can see these mutations. We usually only see those in thyroid cancer, so we're going to use this drug we use in thyroid cancer to target this cancer. And there have been some really dramatic cures that happen from that.
That's a game changer.
Oh, and that's really the paradigm for this whole idea that's coming around of personalized medicine, where you do this for pretty much everything. In cancer, it's very easy to, I don't mean easy, but I'm saying you're able to grab the tissue and study the tissue and make some sense out of it. And there have been generations of drugs that have been targeted at the cancers so that you have a very rich library to select from of what you're going to do, trying to attack the cancers. But when as I said, when you get down to the really detailed level, no two people's cancer is the same. They all, because there are so many different mutations that accumulate, that they're all really a little bit different from one another. And I think that's going to be very much the situation in autism. It really is going to be the autisms. But then again, once you start breaking it up into that many different pieces, it almost doesn't make any sense. It's just to recognize that there are many vulnerabilities that can detune how a system is working so that it's not at its optimum. And the key point about the therapy is you don't have to be able to go in and have a therapy that fixes the specific gene that's out of whack, because what you want to really just do is retune the whole system. And so even if you have a drug that's targeting something that's not been specifically changed in that person, you might still wind up having that be efficacious. That's sort of how a lot of medicines work. So I think I'm very pessimistic about the notion that we're going to be able to go in and find things for all 800 or whatever the number is ultimately going to be. Once you start attacking the integrated function that those genes are playing, then I think there is a reason for optimism. Because as I said, there are mechanisms that we do understand. And I think while we may be early to the game, I mean, some people may say, oh, it's premature to do this. I think it's ethically wrong, morally wrong, not to be trying now. So I think that the judgment call is that yes, it's a far reach, but it's a reach that we shouldn't just sit on our hands and not do something about, because we have this unsustainable trajectory of increasing frequency, increasing costs that are all unsustainable.
Wow. Let's probe some of these areas that we hear a lot about in the
Sure.
news. And I want you, the expert, to help us clarify this.
Okay, all right.
Epigenetics.
Okay.
Any impact here in regards to epigenetics?
Sure, and so what epigenetics means is it means long-lasting modifications of how genes wind up getting expressed, and there are several different ways that can come about. One of them have to do with those chromatin kinds of proteins that I talked about when I was mentioning the different areas that get changed. The problem with epigenetic things are that these kinds of modifications. Because again, remember that the DNA sequence in every cell of the body is the same. But obviously a blood cell is very different than a liver cell, is different than a muscle cell. And those differences in the way the genes are expressed are a result of epigenetic modifications. So while I don't have to agonize over what is the right tissue to get the DNA sequence of a patient, I would have a heck of a time knowing which cell I'm going to want to get the epigenetic marks off of. Even if you say, well, of course, autism is in the brain, and I'm going to argue it's probably not just in the brain. There are a lot of different kind of cells in the brain. And so I still wouldn't know where I'm looking. So I know it's going to step on a lot of toes, but I ignore epigenetics. I think it's a signal that I don't need to find. And basically the point is that when you're in a phenomenally complicated area, you've got to pick where you think the sweet spot is, that there's something you can do about. And I don't view epigenetics as that window right now. Not for something like autism. So it is clearly important. It's clearly an area that's evolving very rapidly, but it's an area that I wouldn't know how to meaningfully address.
We're getting ready to walk the high wire. You ready to walk the high wire with me?
Okay,
Right.
sure.
So is it purely genetic, or are there any kind of developmental social issues here as well?
There absolutely are. It's always been crystal clear. What was a game changer was the recognition of how very highly heritable the disease is. That means that we have very strong statistical information that genes contribute 70-80% of the risk for autism. But we know for sure that it doesn't contribute everything, because and the signature that we get for getting that heritability estimate is based on twin studies. Most easily you could see it in twin studies. So identical twins are really the same person, so that they are genetically completely identical. And then while the embryo is forming, it splits into two. And so now you get two clones of one another. All of their genetic information is the same. They are highly comorbid for autism and for a whole host of diseases. Again, if one identical twin is affected, about 80-90% probability that the other twin will be affected. However, sometimes you have identical twins that are not concordant. One twin will have autism, the other, who is genetically the same, will not.
That's where the environment comes in.
And that tells you, and again, we don't know, the trick is we don't know what that thing, to a geneticist, anything that's not a gene is the environment. So there's a lot of stuff out there that's not genes. So we don't really know what that means. So it's clear that there is a very important variable, and that gives you the hope that you can do something. That's really critically important. My peeper.
That's critically important.
No, I'm going to just silence it. I think we'll survive here. But again, the reason that's important to note is that, for instance, one of the paradigm of the genetic diseases is PKU, phenylketonuria. Every baby that's born gets a heel stick, filter paper, dabbed with a little bit of their blood. It goes to the state lab, and they analyze that to see if the child has this very rare, one in 20,000 kids with phenylketonuria. If the kid has that disease, all you have to do is limit the amount of one amino acid in their diet. Amino acids are components of protein. There's 20 components in the protein. If you limit that one component, they're completely normal. If you feed them like everybody else, they'll have an IQ of 20 or 30.
For the rest of their life, you mean?
For the rest of their life.
They have to get away from that amino.
They have, well, the big impact is in the first 5 years, but you have to, so you sort of say, this is the paradigm of a genetic disease, yet I'm treating it with the environment.
I understand.
And that's what genetics really is. Genetics is telling you how the environment is going to impact the organism. It's a way that we can map what will happen. So the fact that we know we can have this discordance tells us that there's wiggle room. You can go in there and you can find something that you can change the tuning of the system. Now, what are those kind of things? We don't know. We know there are some things that are very potent. So all people are susceptible to botulinum toxin, right? It'll kill everybody. So nobody has a genetic resistance to that. But there are a handful of compounds that very few people are resistant to. And there are compounds where what you'd say, some of the seizure medications, if you give them early in a pregnancy, valproic acid is one of them, causes a model of autism. So you increase the frequency of autism in offspring of mothers who are taking valproic acid. The drug thalidomide, which used to cause, it's like on Life magazine, phycomelia, very, very severe foreshortening of the limbs. It was given to some women in pregnancy. It caused this severe birth defect. But it's also a model that will cause, this is in mice models, the thalidomide will cause what looks like an autism-like syndrome. The valproic acid we know not only in the mice models, but we also know in real human studies that it increases the risk. But there are only a handful of drugs that do this kind of thing. Most compounds in the external world don't have a measurable impact on autism rates. So what is it that's happening? Well, there seem to be critical windows of time very early in the pregnancy when there's this vulnerability. One thing we really worried about is that, you may have seen kids who have one eye patched when they're early on. It's called amblyopia. They have a lazy eye. And so you're going to challenge them to work hard with the lazy eye, because we know that if you don't use your lazy eye early on, your brain closes off your ability to ever use that eye. And so even though the eye is built and works normally, once you get through a critical window, we call it a critical developmental window, you've lost that ability. Now, a big worry was that maybe autism is like that. Maybe you have to have certain things at a certain critical window, and if you miss that critical window, then it's gone forever. And so I don't think that that's the case. I think a lot that we've learned with the animal models tell us that that's probably not true, that we should be able, because then how would you go about treating this, right? Because we can't diagnose autism early. That's a real challenge for us. It's something that our center is trying to work towards, because there are no biomarkers for autism. To diagnose autism, it's a behavioral diagnosis. You have to show these very simplified, stereotyped kinds of behaviors. You have to have some communication problems. So it is a diagnosis that you can only make after a child's 2 years old. So if it were a disease like that amblyopia disease, where you have a critical window, and once that window's closed, you can't fix it, then that would be a very pessimistic situation for being able to treat the disease. As I said, I believe that all the information we've been gathering over the last 5 or 10 years says that that's not the case, that it is very much like a toxic state, that as soon as you remove the offending situation, you can normalize the biology. So that leaves us in a more optimistic situation for being able to treat the disease. I mean, it would be terrible if we ultimately go through and able to figure out these are all the issues that happen, and to do the treatment, you have to do it at the 3rd week of pregnancy.
Yeah.
So what are you going to do there?
Wow.
Then you're sunk. So I think the fact that the animal models tell us that you can reverse what a geneticist called the phenotype. The phenotype is the behavior that you see, the external manifestation of the genetic background. The fact that you can go in and change that, just like we can change PKU, we can change that by changing the environment. You can go and reverse that situation. I think that's a positive take on what's going on
Very much so.
in autism.
Last question. We got 2 minutes left. Got to get this question out.
Yeah, it better be about vaccines.
He knows. That's right. Okay. So mercury causes it, right?
No. I mean, as I said, environment, we don't have a lot of clues about environment, but one thing that has really been studied very, very carefully, and Congress has been very, this is something that we really, really, really know, that autism is not caused by vaccination. And we just had, right here in Southern California, we got a big dose at Disneyland of what happens when people don't vaccinate.
Yeah.
You get bad diseases that we thought were all gone. So we had this big measles epidemic that spread because kids weren't getting vaccinated. And this isn't, impoverished poor kids who don't have access to medical care. This is weird because this is people who have high access to medical care who are electing not to vaccinate. Vaccination, all of the ingredients, the preservatives, all of those things unequivocally do not cause autism. And that's something that we've been able to say with a high degree of certainty. So that's really something that I think that word has to get out there. I mean, people have heard up and down the scandals around the story, the study of 12 kids where the lawyers were paying them to do the studies. It was just...
Oh, wow.
This is the Andrew Wakefield story where, the paper was in Lancet. It has disappeared from Lancet. He was a physician in England. They made him live in Texas now. And so all kinds of consequences have come from this bad study that has unfortunately gotten promulgated by lots of movie stars and other scientific experts. I mean, I don't know why, but movie stars have a very big impact on what people believe.
Yeah.
And so...
and sometimes they do good jobs.
Yes, sometimes they do good jobs, but I'm just saying
Yeah.
that it has had a horrible effect. It's had a horrible effect, and I'd hate to see measles encephalitis come back in this country.
Yeah, it's a good point. It's a good point.
Yeah.
So, Dr. Gargus, a lot of people are going to want to know more about this. Where do we go?
So we have a website. So we're the Center for Autism Research and Translation, and our website is www.autismresearch, all as one long string, .uci.edu. So it's very easy to find us, and there are all different kind of branch points off of there that link one web page to another, so you can find as much as you want about us. We have all kind of brochures and stuff we'll be glad to send people. Look us up.
Dr. Gargus,
Yes.
thank you so much
Well,
for being
thank you,
here.
Carlos. My pleasure. Thank you so much.
Wow, we learned so much. I hope you learned as much as I did. I mean, I couldn't believe how much we've learned. Francis Crick and Watson are excited about all this, too. I'm sure they are. Remember, our motto is simple, everyone. Wherever there's psychology involved, genetically or not, we're going to be there. We'll see you next time.